Hello, scholars. We're going to be talking about Euler's method. And what Euler's method is effectively going to do is allow us to use a differential equation and some sort of initial condition. You can see a very simple differential equation here. Y prime equals x plus y, and y of 0 is equal to 1. And Euler's method is going to allow us to start at this point, 0, 1, and without knowing the solution curve, actually approximate where a certain input and output value is. So let's just say, for example, that this is our picture. This example also, there's a little bit in section 9.2 in your calculus book, there's the same exact thing. Let's just say that this is the solution curve. But we don't know what that solution is. You know, we haven't solved this differential equation, let's say, for the sake of argument. What we do know, though, is that there's a point right there at, that's 1, so that's 0, 1 right there. What we're going to do then is, let's say, for example, that we're trying to approximate y of 2. So we're trying to find what y of 2 is, and what we know is that point. So what we're going to do is, I'm actually going to draw my solution curve a little differently just to make it simpler on the picture. Sorry. Okay. So what we're going to do is when we start at 0, 1, we're going to say that, let's say that 2 is somewhere out here. And again, we don't actually know where this point is for when x equals 2. And that's what we're trying to find, since this is the solution curve, but we don't know it's there. So we start at 0, 1, and we want to move over with the correct trajectory, if you will. Which means, since we don't know what this curve is, the major thing we do know about that curve, though, is we know the slope of the tangent line at that point. And that slope of the tangent line at that point, if we plug in y prime, we'll get y prime at 0 is, well, it's 0, 1 actually, is 0 plus 1 is 1. So what that tells me to do is to head out in that direction with a slope of 1. Okay, so let's just, and you have to eventually stop, right? Otherwise, we would just use a linear approximation, and we'd say, well, I guess maybe this curve could be linear, so just start at the point we have, and you'd head all the way out. Which wouldn't be that bad in this case. You know, it might not be that far off. But let's say we were looking for y of 200 instead. Now this linear approximation can be way off, especially if the curve takes some turns. So we're not going to go that far over. What we will do is we'll name a step size. And you must do this for Euler's method. And by the way, it's Euler, not Euler, if you didn't know that ahead of time. So the step size that I'm going to name here is 0.5. Now what that step size tells me to do is it says, okay, what I want to do is go over roughly 1/2 and then stop. And at that point say to myself, well, what is the solution, or what does the differential equation tell me the tangent line is at that point? Remember, I'm not actually, this point right here is approximately where the function is at x equals 1/2. It's not an exact spot. And because it's not an exact spot, we don't want to further our inexactness. What we're trying to do is get closer to where the curve is. And the way we'll do that is we'll say, well, I wonder what y prime is when x is 1/2. So when x is 1/2, you might say, well, what am I going to plug 1/2 into? Well, what we do is we actually substitute 1/2 into a linear function that represents my dotted line. So we need to have a linear function to represent that. So that linear function at this point is you have to first decide what the slope is. The slope is 1. The intercept is 1. So we get 1x plus 1. And that'll actually tell you where this point is. So at this point, for this particular piece of our function, if x is 1/2, then y will equal 3/2 if x equals 1/2. So for y prime of 1/2, really you can think, since y prime is a function of 2 variables, think of it as y prime of 1/2 comma 3/2, and you'll get 1/2 plus 3/2 is 2. What that tells you to do now is go to your point and go up a slope of 2. Now, how long do you do that? Well, our step size is 0.5. So we're going to go until we hit 1. And you can see in this situation, it's kind of angled us up. And in theory, that will get us closer and closer to the line. At least by the time we end up at 2, we should be closer to the solution curve than we would have had we just followed our initial slope of the tangent line. So really, every time you're just making a slope of a tangent line and then heading up to a point and saying, well, I might be a little off, let me recheck my slope, and then keep going. And obviously, if we made our step size smaller, we would get a bunch of little segments that would really closely hug the function. And you can see a picture of that right. Let me make sure that you can see it well. Right there. Might be a little blurry. It's on the top of page 576 in your text. So we go from there and we see that our slope is 2. And now we want to find, well, what's y prime of 1? But we don't know what the y value is yet. So yet again, we need to look at that segment and say, I wonder what that segment is. Well, we know 2 points, right? We know 1/2 comma 3/2 was on the line, right? And we also now know 1 comma, and we've got to decide there. The slope was 2, right? Yes. The slope was 2, and we know that point was on it. So you can do like point slope form or something like that. Y minus 3/2 is equal to our slope times x minus 1/2. Because we know that point is on this segment. We just don't know what that point is right now. So I guess I'll just simplify this a little bit. Y equals 2x. That's 1 plus 3/2 is 5/2. So now to find what that point is right there, it would be, to find the y value of that point, 2 times, oh, sorry, I think I screwed up there. 2 times negative 1/2 is negative 1, plus 3/2 is 1/2. Sorry. Now we'll put 1 in here, that'll be 2 times 1 plus 1/2, and you'll get 5/2. Which means that point right there is 1 comma 5/2. So we then keep going. 1 comma 5/2 substituted into y prime, and we see 1 plus 5/2 is 7/2, also known as 3.5, and then we go to our point and we say, oh, now I'm going to go a slope of 3.5. And then you continue this process until you've found an ordered pair at the desired point. So a very typical question that IB would ask, they'd start you with a differential equation. Let's just say, for the sake of argument, y prime equals x minus y, also known as dy dx equals x minus y, with the initial condition again of y of 0 is equal to 1. And they might say approximate y when x equals 10 with step size 0.4. So in this case, it's going to be a lot of steps. There's 0.4, you have to keep going up 0.4, starting from 0 all the way until you get to 10. So you'll make a table of values, and you can see different tables of values. Again, you can see a calculation done similar to that on page 576 in the text. But you just keep stepping up slowly and readjusting your tangent line until you get a bunch of little linked together segments that are closely mirror the curve. And again, the smaller the step size, the better approximation.